So Isaac knows how to do them all, for example. So the baseline is he'll present everything. But then I have a really big problem for you tomorrow, and another really big problem for you hopefully on Wednesday, and they're both solvable by Friday. Right, Cecile? Okay, so there are some papers here which you can, this is on the BUC webpage already, so there are some papers there you can browse if you're interested in some more of the material. So just today, I will whiz super fast through some bits and pieces from Levy process which you'll not really need to know, but it'll be useful. And I think a lot of you know it anyway. So you know what a Levy process is. You know the Levy-Hinchin formula. So I've defined my Levy process to have a slight little twist on it. I've got this extra term here. So there's your usual linear quadratic and the jump part here. But I've added this constant here, and this corresponds to the case that we're killing the Levy process at an independent and exponential time with rate q. So always when I talk about Levy process implicitly, I may or may not mean with a killing after an independent and exponential time. So if you've not seen Levy process before, this is a linear drift, this is quadratic, and this is the coming from path discontinuity. So roughly speaking, you'll have a jump at size t of size dx with this probability. This is the measure pi here. But I'm pretty sure most of you have been through Levy processes before. In one dimension, so this is high dimension, so these are in a product, so we'll kind of mostly talk about one dimension and occasionally high dimension. This is the case of a subordinator, so this is when its paths are monotone. So again, the killing component is there. We prefer Laplace exponents in that case. And then there's drift component, and again, the jump structure is slightly easier to describe. This is called a Bernstein function, and this collapses slightly because it has paths of bounded variation, so the sum of the path discontinuities add up, so this is not as complicated as it needs to be. Okay, so we'll see some examples of subordinators also on the way. I think you've also, in fact, here's a subordinator right now, one that you need to know about. This is the case of a stable subordinator. So it's an increasing Levy process without killing in this example. It has this scaling property, a bit like Brownian motion. You multiply by a constant in space, and if you scale time, so you dilate space and you also dilate time in an appropriate way, the alpha here is the index of self-similarity, which is one of the parameters defining the processes. So this scaling leaves the process untouched in law. So you take the process, you stretch it in space, you stretch it in time in this way, and it's still equal in law to itself. Alpha has to be between 0 and 1. The Bernstein, the Laplace exponent, it turns out to be rather nice, lambda to the power alpha, and the jump measure specifically takes this form. This is a constant. This is 1 over x to the 1 plus alpha. So you can see here the rate of the jumps is massive when x is terribly small, and otherwise for large jumps it's quite rare. So this conforms with our idea of having lots of small jumps and the occasional big one. This class here you're going to see a lot of throughout the course. This is a Levy process whose characteristic exponent may or may not have a killing term. It depends if we set theta as 0, it depends what the values of beta and gamma hat and beta hat are. But this is called a hypergeometric class of Levy processes. This was not really known too much until a few years ago, very recently. It was defined by Juan Carlos and Alexei Kuznetsov, and it's called hypergeometric because it has this nice Levy density, so the Levy measure pi has a density with respect to the Lebesgue measure. If you throw aside the constants and the exponential, then it's fundamentally it's a hypergeometric function of e to the minus x. So an f21, a, b, c, and then the argument is e to the minus x. So although the Levy measure looks nasty, the characteristic exponent is very nice, which is kind of important because of this phenomena, which is the Vena Hop factorization, which is extremely useful if you can get it. So the Vena Hop factorization says every Levy-Hintschen exponent, every characteristic exponent factorizes into kappa minus I theta kappa hat plus I theta, where each of the kappas are Bernstein functions, so they are Laplace exponents of subordinators, and these subordinators have a heuristic meaning. So if you look at the path of the... Is this electronic or... Can I draw on this?
I don't know.
Yeah? Here? What do you mean you don't know?
No, well, I don't know.
Or you can, but we don't know how.
Am I allowed to draw on here?
Yeah, I think so.
Okay. So if your Levy process is squiggling around, of course, with path discontinuities, and you monitor the running maximum, which of course will have discontinuities because this blue path should have discontinuities, and we project the range of the green path onto the vertical axis, then actually this green path corresponds also to the range of an increasing Levy process, a subordinator, and that's the one here that appears here, this kappa that appears here. Why would it have killing in it? Well, it might have killing because this has killing. This may not have killing. If this doesn't have killing, this may still have killing, and that's because it may be a Levy process that drifts to minus infinity. If that happens, then of course I have a last maximum. This flat line's here, so I should stop the range of this subordinator somehow, and that's coming from the killing. So what's going on is, to get to the subordinator, I'm taking the excursions and I'm just deleting them and then pushing the path up, shunting the path up, and what you get left is the subordinator. So obviously this guy here is what you get when you monitor the range of the infimum, the running infimum, except you need to flip the range onto the positive half line to get a subordinator, to get an increasing path. Now, this minus I theta and plus I theta, these are the analytic extension of these. So these are Laplace objects, Laplace exponents, but this is saying that these things can be analytically extended, and you take the analytic extension on the lower imaginary axis on the upper imaginary axis. And in fact, the factorization is unique according to that analytic extension. So there may, of course, be other Bernstein functions that do this, but it's unique in the class of Bernstein functions which can be analytically extended into the upper and lower half plane, respectively. And this case is particularly nice, this hypergeometric, because there you can see exactly one of the Vena Hop factors and the other Vena Hop factor. This is why this is a particularly nice class of Levy process. I'm slightly lying to you. It's not entirely true that the factorization splits here. It depends on the parameter regime, but let's not worry about that for now. So heuristically, these are the two Vena Hop factors, this one and this one. And these are coming from what are called beta subordinators, and they are subordinators which have rather nice they have rather nice Levy measures, so there's something like e to the power something x divided by e to the something x minus 1 to the power 1 plus something dx. And I can't remember what the somethings are. But fundamentally, if you look at the ratio of the gammas, you can think about a beta integral, and you can manipulate the beta integral to look like this. Forget these terms, or possibly you need this term, but certainly forget this term, and that would tell you what this Levy measure is. You'll end up with something like this after some changes of variable. That's not an exercise, but it could be. Okay, so then, of course, stable processes are the ones that I'm going to talk about a lot for this week. So these are Levy processes which intersect in the class of self-similar Markov processes. So I seem to have brought a slide forward and not thought about the consequence of bringing the slide forward from an older talk. So what do I mean by a self-similar Markov process? I mean precisely this property that we had before. So if we scale it, if we dilate the process in time, and then we scale time accordingly with c to the minus some index alpha, what I see is a copy of itself in law. So anything which remains in the class of Levy processes and has that scaling property is what is called a stable process. Brownian motion is included if alpha is 2, but we don't want Brownian motion. I'm going to try and avoid diffusions for the whole week. I don't want to talk about anything that's diffusive because there are other ways of dealing with diffusions. And in general, this class of Levy process has to have a characteristic exponent of this form. So this, of course, includes the example of the increasing subordinator I gave you, but there's much more in there. There are processes that jump up and down. There are processes of one-sided jumps, but which have unbounded variation, so they still move up and down, even though they only jump in one direction. But generally, the characteristic exponent is of this form. It has two parameters, the alpha and the rho, and fundamentally, the exponent is mod theta to the alpha. And then, depending on whether theta is plus or minus, we somehow give a different constant on either side of the real line for theta. This other parameter rho is the positivity constant. It's written in terms of t. It doesn't need to depend on t because of scaling. By this scaling property, you can show it's the same. It's in distribution equal to the probability that x1 is positive. So it doesn't depend on t. You'll see lots of hats hanging around in my lecture notes. So a hat just means the negative of the corresponding process. So if it's a x hat stable process, it means 1 minus the minus the stable process. So of course its positivity constant is just 1 minus rho. Rho hat is 1 minus rho. And the Levy density corresponding to this, so you've already seen the example of an increasing path. So it looks like this. So it's very similar. Here I'm saying, depending on whether we want to look at up jumps or down jumps, we have a different constant rate. And you can see now why I'm saying to have jumps in both directions, alpha rho and alpha rho hat must both be between 0 and 1, because if one of these hits 0 or hits 1, then it will kill off this constant. So it will make it spectrally one-sided. It will put the jumps only in one direction. The case of a subordinator was alpha less than 1 and rho equal to 1. Right? So we have subordinators, everything is on the positive half line. So that would make rho hat 0, and that would kill this constant. So we would get back to the expression we had for the subordinator. But in general, I'm largely going to treat the case that we have up and down jumps. Okay, so you can see here that the scaling, the self-similarity is already present in the exponent. So as an exercise, you can check that if you scale the process in space, that's equivalent to replacing theta by c times theta. And if you scale it in time, so you remember the exponent fulfills this relation, so it's e to the minus psi t. So scaling in time is equivalent to changing t by c to the minus alpha t, which is equivalent to multiplying psi by c to the minus alpha psi. So the space-time transformation is this, and if you perform this at the level of the exponent, you see you come back to where you started with. Okay, so the sine of theta doesn't care about all this business with c. The only thing is this mod theta to the alpha. Okay, so you can already see the scaling in the Levy exponent. I think I'm going around in circles here. There's a slight adjustment to what I was saying. So before I said when you scale in space and time in such a way it's equal in law to itself, that's starting at the origin. So actually more generally, the equivalent statement when you start not from the origin, so start from some x, so I've added another index here, which is where you start from. I'm saying if you do the scaling in space and time, starting from x, then the resulting process is equal to itself. But of course, I have to start now from cx and not from x. Okay, so there's no way I can multiply x0 by c and start still from x. I'm starting from c times x. When x is 0, of course, then they're the same object. Okay, so some Levy processes explore space. As they move around in space, they explore space in different ways. So one question you can ask is, can I visit a point? You tell me a point in space, can the process pass through that point with positive probability? I appear to have, again, caused chaos by reordering my slides. So there's a notion of creeping which comes from, I've mentioned it here actually. So there's a notion of creeping which comes from when you pass from below to above in one dimension a threshold, and you do so by hitting the level. So here I'm saying this is the first time the Levy processes, that should be a strictly greater than. So I do apologize, that should be greater than here. So of course you could jump over a threshold, but there is the phenomenon that you pass upwards above a threshold by hitting it. This is called creeping. So it means the probability you pass the threshold by hitting it is positive. And the way to determine whether that happens is to go back into the factorization, look at the ascending ladder exponent, as it's called, kappa, and check whether it has this drift term here. Because essentially what's going on is, in terms of the subordinator, this is all the jumps, this is the killing, and this is interlaying between the jumps a kind of a linear drift with speed delta. And so you're not able to the Levy process is not able to cross a threshold by hitting it unless the green process can cross a threshold by hitting it, because the green process is all the new maxima. So when you cross a threshold, you're making a new maxima at that moment. So if the green process can contain the threshold x, if it's in the range of the green process, then certainly the Levy process has hit x. So the question of creeping up for the Levy process is the question of creeping up for the subordinator of the ascending ladder process. And that intuitively, it's quite clear that this is the determining factor, whether you've got drift here, right? So you're not really going to manage to get upwards across by a jump. You could, of course, jump onto it, but that's going to be a zero probability event. So the only way is, and you could, of course, accumulate lots of little jumps and hit the threshold, but again, that's too difficult. So intuitively, the only way is somehow in the range, you've got some kind of Lebesgue heavy component to the range of the process, and it's the probabilities that you land in that Lebesgue heavy part of the range. So when you're asking the question, can I ever hit a point? Well, of course, you can do it by creeping, but it's not the only way. So you can hit a point by crossing upwards continuously, but of course, not necessarily. The other way to do it is by accumulating to that threshold. So by jumping up and down sequentially above and below it and accumulating your trajectory to that point as a kind of limit. Even though it has right continuous left limit paths, I can still limit to that threshold level x. So it necessitates me to come across the threshold infinitely often. Well, the criteria for creeping or this type of behavior is determined by this integral test. It's quite an old result. Okay, so if you know what your exponent is, stick it in, integrate it. If it's finite, you can do it. If it's not, you can't. And if you can, then you can even go a bit further and work out what the hitting probability is. So the probability starting at 0 and hitting x is the ratio of u of x over u0, where u of x is, you might think of this as the inverse Fourier transform of 1 over the characteristic exponent. Okay, so there's lots of magic hidden inside of this characteristic exponent. It's called the characteristic exponent because it characterizes the process, and all of these theorems results are telling you how to extract information about fine path properties from this one object that characterizes the process. Okay, so here's your first exercise. This is piss easy. Prove that if alpha is between 0 and 1, so again, remember I always want up and down jumping stables. Right, so prove that this thing can't hit points if alpha is between 0 and 1 inclusive, and if it's between 1 and 2 inclusive, it can, and it can with probability 1. 6 o'clock, I want to see the answer on the board. By the way, one thing I should say about this thing here, when alpha is 1, in order to respect this scaling property, I must have rho is a half. There's a very special thing that happens when alpha is 1. It has to be symmetric, the process. I don't need symmetry when alpha is not 1, but when alpha is 1, in order to preserve the self-similarity, I guess it comes back to this exercise here. You need rho is a half. Okay. So that was a whole course condensed into 10 minutes. So now let me tell you about self-similar Markov processes. So all I've done now is, you remember a stable process was the intersection of a self-similar Markov process and a Levy process. Forget the Levy process bit and just say, let's go high dimension, let's go to RD. Give me a Markov process, a regular strong Markov process. If you don't know what regular means, don't worry about it. On RD, probabilities Px. What's its defining property apart from being Markovian? It scales in the way that we've seen before. For any alpha positive. Okay, so a self-similar Markov process is Markovian, strong Markovian, regular strong Markovian, and it scales in the way that a stable process scales. So it doesn't have to be a stable process because I've dropped the requirement of being a Levy process. Okay, so now there's a ton of exercises here for you to do. I want to see the answers by 6 o'clock. Take a stable process, so you know a stable process is self-similar, it's in its definition. So first of all, take the running minimum and look at the pair and show that this is Markovian. So all the time we should be proving regular strong Markov, but I'm going to give you an easy ride here and just go with the checking Markov property. So check that the pair is Markovian when this is, in fact, I'm saying here this is true for all Levy processes, actually. And then, because this pair is Markovian, I'm claiming that you can check am I even proving it here for? I've even done it for you. So this exercise you don't have to. So when alpha is 2, I mean, you scrub that. You don't need that. Any alpha, any stable alpha will work. I think there's the proof for you. So done, tick, right? So you don't need to do that exercise, Osvaldo. You're off the hook. All right. So look what I'm doing here. I'm saying if I scale in space and time for the vector pair, so what's the definition? I put the definition in. So all I've done is I've changed the index and put the c to the minus alpha onto the index here. And then I invoke the fact that the stable process is scalable, so it's equal in law to itself when it scales. So the pair, because it's a functional statement that the entire path when scaled is equal in law to itself. So here is a functional of the entire path. Here's another functional of the entire path. So because of the scaling of the stable, the pair must be equal in law to itself. So I've already done the first exercise for you. You can go to sleep for 2 more minutes, Emma. So now, next exercise, prove that this is Markovian. So this guy minus the minimum of minus x and its infimum, and that it's self-similar. So somehow you need to combine the fact that this pair is Markovian, the scaling property here, push it through and show me that this object is a self-similar Markov process. 6 o'clock today, I want answers. Here's another one. Take the stable process again and just get rid of it, send it to 0 when it jumps below the origin. Show me that this is a self-similar Markov process, this time on the positive half line. 6 o'clock today. This one here, take the symmetric case of a stable. It has to be symmetric. And then now take the modulus of a symmetric stable. Show me that this is a self-similar Markov process. And I'm actually saying because of rotational invariance, so actually this statement works in high dimension as well. You could even take a symmetric high dimensional stable. Because of the rotational invariance, that's why it's Markovian, so that it needs a proof. In one dimension, rotational variance is equivalent to reflection, of course. So the negative is equal to itself. That's what rotational invariance is in 1D. Okay, so by 6 o'clock, I want answers. Okay, so here's another example where you can dig out a self-similar Markov process. So thinking about the last example, if you go back to the diffusive case, despite the fact I said we're not going to dwell there. So if you take a d-dimensional Brownian motion, specifically 3-dimensional, you look at the radial distance from the origin, you know, or you should know, that it's a Bessel process, but it's also equal in law to a 1-dimensional Brownian motion conditioned to stay positive. So this is hinting that the modulus of at least a Brownian motion being also a conditioned 1D Brownian motion, this is hinting that this should also be self-similar, at least for some special cases. Well, here's a little exercise. Just prove that that is a martingale. This appears in the sense of the change of measure. So I'm saying on the one hand, look at the modulus of this, and on the other, the conditional limit. In this sense, the infimum at time t plus s of the Brownian motion being positive in 1 dimension. Take the limit on an event up to time t, you'll get this dupe H transform here. I'm asking you to prove that's a martingale. I'm not so interested in this exercise so much, so I'll let you off this one. The point I'm really getting to here is that this should be a self-similar Markov process because it agrees with the modulus of a three-dimensional Brownian motion, which by the previous exercise you will have proved by 6 o'clock that that is a self-similar Markov process. So could we take a stable process and condition it to stay positive instead of a Brownian motion and conclude that that's a self-similar Markov process? So how do you condition a stable process to stay positive? So again, remember we have this Vena Hop factorization. The answer comes out of the Vena Hop factorization. In the stable case, the factors are rather easy. They're two stable subordinators. You're not surprised that the Vena Hop factorization of a stable are two stable subordinators. One has index alpha rho, the other has index alpha rho hat. Okay? Now, general theory says if you want to condition a Levy process, be very careful. A stable process is a Levy process and a self-similar Markov process. So I'm flipping between using facts about it as a Levy process and facts about it as a self-similar process. So here's a fact about all Levy processes. So just like the Brownian motion, to condition to stay positive, I mean it in this sense, and the limit appears as a Doob H transform, but no longer with x as the martingale function, now with the descending ladder potential. So it means 1 over the descending ladder exponent. Take the inverse of this as a Laplace transform, or take the inverse Laplace transform. It gives you a measure, and the distribution associated to that measure gives you a function that appears as the harmonic function here. In the stable case, this is lambda to the power alpha rho. So this is an easy inversion. The function u hat is just x to the power alpha rho hat. So this appears as a rather nice function. Remember, when alpha is 2, we have to have symmetry. It's Brownian motion, so that becomes a half times 2. That's 1. That was the function we saw before for conditioning Brownian motion to stay positive. But for a stable, we replace it by x to the alpha rho hat. That's the take-home message. So the question I now have for you is a stable process conditioned to stay positive a self-similar Markov process? And of course the answer is yes. Yes, because it's Markovian, because it's a Doob H transform. This preserves the Markov property, as do all Doob H transforms. And scaling, so what would I check? I would check that, this might be helpful for some of your exercises, I would check that if I look at a functional of the path, say up to time t, under the change of measure, I scale in space and time, put the Doob H transform in. So when I put the Doob H transform in, this function is a function of something up to time c to the minus alpha t. So I put in the density at c to the minus alpha t. Right? Now the magic here is that because of this polynomial form, I can multiply by c to the power alpha rho hat and c to the power alpha rho hat here. Okay? When I do that, I see I'm looking at, also here I can multiply by c, I'm looking at a functional here, all this stuff here is a functional of c x, c to the minus alpha up to time t, under the original measure when it's a stable. So I can invoke stability, I can invoke the stability of the stable process. All these functionals here are equal in law to the copies of themselves, except changing x to cx. Remember, we multiply on the bottom by c to the alpha rho hat and the top by c to the alpha rho hat to make that transform, also in here. So I'm left with a c to the cx to the alpha rho hat, which is great because when I make the scaling transform, this guy now starts at cx, and rather conveniently, I have the cx down here below, which is what this should be doing at time 0. So by definition, this brings me back now to the condition process initiated at time cx. So this is one way to check the scaling property for the condition process. Okay, so unlike the Brownian case, the condition stable is not the radial component of a higher dimensional stable, for example. Okay, so you've seen now many examples of self-similar Markov processes. I've built them all by taking the one example we know, which is the stable, and making path transformations of the stable process. When should I stop? About 1/2 past? About 1/2 past. Okay, so all that's very much concentrated around one family of self-similar Markov processes. What about the general theory? So let me just introduce some notation. So Xi will always be a Levy process with killing, the usual exponent appearing here. It is going to be this integrated exponential Levy up to time t. I infinity, well, this has a limit point-wise, so I infinity is just the limit, almost sure limit. And then this phi t is the inverse of this. This is going to be a clock, a new clock, a path-dependent clock. So Lamperti's transformation said, if you manage to find a positive, so this is only about positive self-similar Markov, so it's not going to tell you the story of the full d-dimensional class. This is the half-dimensional class. If you give me a positive self-similar Markov process with index alpha, then I can find a Levy process of some type such that I can write the self-similar Markov process until it first hits the origin as its initial position e to the power xi with this time change. And the time change is what I call endogenous, because it's the inverse of the integrated exponential, and the integrated exponential is a clock which depends on where the xi itself goes. So the time change, it depends on where this xi is going. And this representation actually characterizes all self-similar Markov processes into one of three categories. So the first category is, well, you remember that all Levy processes have a trichotomy like random walks. Either they drift to infinity, they drift to minus infinity, or they oscillate. Okay, so one category is where there's no killing on the Levy process and it lim-sups to infinity. That means either it drifts to infinity or it oscillates. If that's the case, then you can go back through this time change and check that you will never be able to hit the origin. Right? The zeta will be infinite. And it doesn't matter where you start from, it will be infinite with probability 1. Of course, the scaling property is what's giving that. And so you have a path here which somehow lives forever on the positive numbers. So this is case 1. You have something which just mooches around on the positive half line, and it can be described like this, e to the xi phi. By the way, sometimes if I were to pretend that xi, if I were to index like I've indexed z, z is indexed with x to say it starts from x. If I would say xi starts from log x, I could put that x up into the exponent, add the log x, and just absorb it into the xi, and put the bracket log x up there. So here when I write this, I'm thinking of xi starting at log x, if this guy starts at x. And what about this time change here? Well, if you think about this x to the minus alpha t, if you go back over here, when I've got a start point of log x here, if I bring it out, so it's additive because it's a Levy process, it gives me an x to the power alpha. So I would have x to the power alpha I, but I built from the xi starting from 0. And if I pop that over on the other side, the x to the alpha, it gives me the phi t x to the minus alpha that you see here. So if I were to take my xi and say, well, actually, my xi is starting, it's inherent that the xi is starting from log x, not from 0, then I could scrub this x here and scrub that x there. Right? So I guess what I'm saying is this. I can write it like that, or I can write it like this. And it's the same thing. Meaning this starts from x, this starts from log x. That representation there, xi starts from 0. Okay, so one example is when this guy limits up to infinity. Next case is when the limit is minus infinity, so it doesn't drift to plus infinity and it doesn't oscillate, but it drifts to minus infinity. And this will cause e to the minus infinity goes to 0, so this will cause this to go to 0. We need to check that the time change is almost surely finite. That's what it's saying it does. And it approaches the origin continuously. So somehow, in the second case, because of the Levy process drifting to minus infinity, it's jumping around, but it is slowly working its way down to 0, almost surely, irrespective of the starting point. Again, that's all just scaling coming through. And the third example is the case where so in these two we've had no killing on the Levy process. So the third example, just put killing on. So this corresponds to when psi has killing. And then what happens, so I don't care about the drift of the Levy process. What happens is z moves around. At some point through the time change, so at some point through the time change phi, this exponential clock rings, and then I'm going to make a symmetry state of minus infinity for psi, and that will force z to suddenly jump to 0. Right? So if we agree e to the minus infinity is defined to be 0, if we make the symmetry state of the Levy process minus infinity, then this third category, it will suddenly drop to 0. Right? So at the time scale of psi, this happens at an independent exponential, but that gets worked through phi on some random time. And the theorem is telling you that will necessarily be almost surely finite, and you will have a discontinuity at the lifetime here. Here we have a continuity, it works its way down to 0. Here it just boop, drops to 0 with a discontinuity. So that's if you're walking down the street, you trip over a positive self-similar Markov process by accident, you pick it up, and it necessarily, you start picking it apart, and it necessarily, you find that you'll have a psi, a Levy process, which does one of these three things. The converse is, I come in one day and I give you a Levy process, and you make the transformation with that Levy process. What have you made? You've made a self-similar Markov process. Okay, so there is a bijection between the class of self-similar Markov processes, positive self-similar Markov processes, and killed Levy processes. One is synonymous with the other. Okay. Now, I've given you several examples of self-similar Markov processes built from the paths of stable processes. So, for example, I gave you this one. By 6 o'clock, somebody will have proved this is a self-similar Markov process. Right? So this is an example of that fits this category. So he's happily moving on. So again, be very careful. The Lamperti transform has inside of it a Levy process. However, in this example is built from a Levy process, the stable process. So X is a Levy process. I've manipulated its path. I'm claiming a self-similar Markov process, and therefore has a decomposition where this is another Levy process. So I've got a Levy process hiding inside of a Levy process. Now I'm claiming this looks like this. This guy moves happily as a stable process. You come along and say, as soon as you jump over the origin, that's the end of this story. I'm just keeping it at 0 then. Right? So it must fit this category. Why doesn't it fit this category? Remember, we saw the descending ladder process was a stable subordinator. Remember, the stable subordinator has no drift, so it cannot creep downwards. It cannot cross thresholds continuously downwards. So it must pass by a jump over the origin. So this guy is moving nicely as a stable, and then it jumps over the origin, its infimum goes negative, and you say game over, stay at 0. So it has to be by a jump because we can't creep downwards. If we could creep downwards, we might see this type of behavior. So it has to fit this category here. I'm practically doing the exercises for you now. Okay, so I'm claiming that inside this self-similar Markov process by the Lamperti transform, there is a Levy process. By Lamperti's theorem, it's called Xi star. And I think in my next lecture, I'm going to work out what Xi star is explicitly. And just to whet your appetite, it's a hypergeometric Levy process. So you should crap your pants at this point and think that's amazing. It is amazing. It's unbelievable. Not only is this unbelievable, it's going to be even more unbelievable that you're going to see lots more of these hypergeometrics appearing hidden inside path transformations. Okay, have you got any questions? So remember your exercises, I want to see by 6 o'clock. I want answers on the board. These exercises here. No?
No?
No. You get to go home at 6 if you do them all by 6. Okay.
One question.
Yeah.
So if you take alpha stable Levy process and you do the Lamperti transform to get a self-similar Markov process, the Lamperti transform that you do, you can take another parameter than alpha, I guess, beta.
So I think what you're asking me, so first of all, a stable is not necessarily positive, but let's take a subordinator just to make your question make sense. So I think what you're really asking me is, oh, this is mobile. What about raising to the power beta? So if I took you've just given me another exercise. Thank you very much. One more exercise, thanks to Arno. Take a stable subordinator, raise it to the power beta, prove that this is a self-similar Markov process. This is your question, right?
I'm not sure.
It is now. So I could do that to a stable, but in general, but it's going negative. So far we only know about positive.
Okay, yeah.
So I've taken the special case of
I
a.
keep my question for the next.
Yeah,
So,
I think there's more. There is more coming about signed processes. Any more questions? Bearing in mind that may add to the list of exercises.
Ask questions. Yeah.
So shall we thank the speaker?